Senior High School Pre-Calculus Core Subject. Parabolas. Learning goals. At the end of the lesson, the student is able to: Number 1. Define a parabola. Number 2. Determine the standard form of the equation of a parabola. Number 3. Graph a parabola in a rectangular coordinate system. And number 4. Solve situational problems involving conic sections on parabolas. Definition and equation of a parabola. A parabola is the set of all points xy in a plane equidistant from a given fixed line called the directrix and a given fixed point called the focus. To illustrate, let's say that this dashed line is our directrix and this point F is our focus. We try to plot several points on this graph in such a way that they satisfy the definition. That is, the location of these points must be of the same distance from the focus and from the directrix. If we continue plotting points and connect these points using a smooth curve, then we'll be tracing the pattern of the parabola. Geometric properties of a parabola. Principal axis. The principal axis is the line through the focus perpendicular to the directrix, also called the axis of symmetry. Vertex. The point V, considered as the tip of the parabola, which is the intersection of the parabola and its principal axis. From the figure, the distance of the line segment FB is equal to the distance of the line segment DB. From henceforth, we shall call it A, i.e., the length of the line from the focus to the vertex and from the vertex to the directrix. Latus rectum, also called the focal width, is the line segment LL', perpendicular to the principal axis, passing through the focus. The length of the latus rectum is 4 times the length of the line segment FV. Standard equation of a parabola. Where a parabola is drawn, it will have a focus F with coordinates MN and a directrix. The standard equation of a parabola can be deduced following the definition of a parabola. Let's say there is a point P on our parabola with coordinates xy. Now we know from the definition that the distance of point P from the focus F is the same distance of point P to that of the directrix. And that is, the length of the line segment FP is the same or equal to the length of the line segment PQ. Now before we derive the standard equation of the parabola, we take note of all the points introduced in our figure and their coordinates. First, the coordinates of our focus F is MN. The coordinates of the vertex V is HK. The coordinates of point D, which is the intersection of the directrix and the axis of symmetry, its coordinates would be M, negative A. The coordinates of our point P is XY, and the coordinates of Q is X, negative A. We now derive the standard equation of a parabola. Take note from the definition that the length of the line segment FP is equal to the length of the line segment PQ. We re-express this equality of lengths in terms of the distance between the points F and P and the points P and Q. Take note that we have used point P as our reference point for expressing the distance between F and P and the distance P and Q. By the distance formula, the distance between F and P is written as square root of x minus m square plus y minus n square, which is equal to the distance between P and Q, which is written as square root of x minus x square plus y minus negative a square. Of course, y minus negative a becomes y plus a, then square. And of course, x minus x becomes 0, so that would cancel out. Then squaring both sides of this equality to remove the square root sign, then we'll have x minus m square plus y minus n square equals y plus a square. Next, we perform the square of binomial for the binomials y minus n and y plus a, resulting into y square minus 2ny plus n square and y square plus 2ay plus a square. We then transpose the terms y square minus 2ny and n square to the right-hand side of the equation. Take note the change in signs. Notice that we can cancel out y square and negative y square. We then sort the remaining terms in such a way that we can group 2ay and 2ny together and a square and negative n square together, resulting into 2ay plus 2ny plus a square minus n square. Notice in the first two terms, we have the common term 2y that we can factor. Doing that, we have 2y times a plus n. And also we can group a square and negative n square as a difference between two squares. What that means is that we can factor a square minus n square into a plus n and a minus n. Factoring out a plus n would result into 2y plus a minus n times a plus n. Notice that the group a minus n is preceded by a positive sign, which means we can simply drop the parentheses. Now, since the length of the line segment FV is equal to the length of the line segment DV, which is equal to A, we can see then that the vertex with coordinates HK is the midpoint of the line segment FD by definition of a parabola. Therefore, the coordinates HK can be computed as the midpoints between the coordinates of F and the coordinates of D. That is, m plus m all over 2 and n plus negative a all over 2, which results into m and n minus a all over 2. What that means is that h is equal to m and k is equal to n minus a all over 2, which implies then that n is equal to 2k plus a. We then continue as follows. We then replace n by the expression 2k plus a. We simplify all distributions and combine like terms, resulting into this expression, from which we can factor 2 from each, resulting into 4 times y minus k times k plus a. Note that if the vertex is at the origin, then the equation becomes x squared equals 4ay, since h and k become 0. Therefore, the last result of the derivation simply includes a translation of locations of x, y, and a from the origin, and should have no effect on the distances of the directrix to the vertex or the vertex to the focus of the parabola. This is now the standard equation of a parabola for a parabola whose vertex is located at the origin. If we try to include a translation from the origin, then this equation becomes x minus h squared equals 4a times y minus k. We further note, for emphasis, that the term 4a represents the length of the latus rectum and a is the absolute distance from the directrix to the vertex, which is also the distance from the vertex to the focus. It is better to use the form of the equation of the parabola shown below to avoid confusion where a is interpreted as an absolute distance. General equation of a parabola. The general equation of a parabola which opens upward or downward is ax squared plus cx plus dy plus e equals 0. The general equation of a parabola which opens to the left or right is by squared plus cx plus dy plus e equals 0. Notice the exchange of the terms x squared and y squared from both equations. For both cases, A, B, and C are non-zero constants. Example: if the vertex of the parabola is at the origin, that is, the coordinates hk is equal to 0, then the standard equation x minus h squared equals 4a times y minus k becomes x squared equals 4ay. Note that a is an absolute measure. Given this equation x squared equals 4ay, there are two possible ways on how to draw our parabola. One is that the parabola opens upward, and the other one is that the parabola opens downward. For a parabola that opens upward, this is the case wherein the directrix is below the vertex. Conversely, if the directrix is located above the vertex, then the parabola opens downward. A parabola that opens to the left or right has the standard equation y minus k squared equals 4a times x minus h, which becomes y squared equals 4ax if the vertex is at the origin. For a parabola that opens to the right, this is where the directrix is located to the left of the vertex. On the other hand, a parabola that opens to the left, this is when the directrix is located to the right of the vertex. Determine the focus and directrix of the parabola with the given equation x squared equals 12y. Sketch the graph and indicate the focus, directrix, vertex, and the axis of symmetry. For the solution, we first note that 4a is equal to 12 in the given equation, which implies that a is equal to 3. Since the equation is in terms of y and has the form where the coordinates hk is equal to 0, then the parabola therefore opens upward with its vertex at the origin. Let's try to draw our parabola. So we have a parabola that opens upward whose equation is x squared is equal to 12y. The vertex is at the origin, and the focus is at point 03, and the directrix is the line y equals -3. Determine the focus and directrix of the parabola with the given equation x squared equals -6y. Sketch the graph and indicate the focus, directrix, vertex, and axis of symmetry. As with the previous example, first we take note that the term 4a is equal to -6 in the given equation, which implies that a is equal to -3/2. And since the equation is x in terms of y, that means that our parabola is either opening upwards or downwards. Now, to know whether the parabola opens upward or downwards, we try to locate our focus, our vertex, and our directrix. Since we already computed for a, and a is equal to -3/2, that means that the coordinates of our focus should be at 0, -3/2. This implies that the parabola actually opens downwards. And therefore, the line of the directrix should have the equation y equals 3/2. Determine the focus and directrix of the parabola with the given equation y squared equals 8x. Sketch the graph and indicate the focus, directrix, vertex, and axis of symmetry. As with the previous examples, we start the solution by taking note that 4a is equal to 8 in the given equation. Therefore, a is equal to 2. And we also take note the form of the equation y squared is equal to 8x, which is y in terms of x. This means that our parabola either opens to the right or to the left. To know whether the parabola opens to the right or to the left, we try to locate our focus, our directrix, and our vertex. Since the form of the given equation means that the vertex is located at the origin, this means that our focus is actually at the location 2, 0, which implies then that the parabola opens to the right. And our directrix therefore has the equation x equals -2. Determine the focus and directrix of the parabola with the given equation y squared equals negative 4x. Sketch the graph and indicate the focus, directrix, vertex, and axis of symmetry. As with previous examples, we take note that the term 4a in the given equation is equal to, this time negative 4, which implies that a equals negative 1, and that the equation is y in terms of x, which means that this is a parabola that opens to the left with its vertex at the origin. Therefore, the focus of this parabola would be at the point negative 1, 0, the vertex at the origin, and the directrix would have the equation x equals 1. Just a quick summary. From the examples, we can generalize that a parabola opens upwards whenever the equation is x in terms of y, i.e. x squared equals 4ay, and the term 4a is positive. A parabola opens downward whenever the equation is x in terms of y, i.e. x squared equals negative 4ay, and the term 4a is negative. A parabola opens to the right whenever the equation is y in terms of x, i.e. y squared equals 4ax, and that the term 4a is positive. A parabola opens to the left whenever the equation is y in terms of x, i.e. y squared equals negative 4ax, and that the term 4a is negative. Since the form of the equation is for the vertex to be at the origin, the focus will be a point of the form f0a. This is for parabolas opening upward or downward, or the focus would be of the form fa0. This is for parabolas opening to the right or left. As for the directrix will have an equation y equals positive or negative a. This is for parabolas opening upward or downward, or the directrix will have the form x equals positive or negative a. This is for parabolas opening to the right or left. Finally, though not mentioned in the examples, it should be obvious that the axis of symmetry is either the x-axis or the y-axis, since the vertex of the parabolas is at the origin. Find the standard and general equation of the parabola with focus at negative 2, 4 and directrix y equals 1. Let's try to illustrate what is being described. First, it is said that the focus is at point negative 2, 4, and the directrix has the equation y equals 1. Therefore, this dashed line would represent our directrix. Point D represents the point of intersection of the axis of symmetry and the directrix. And a point midway between F and D would be the vertex of the parabola. In order to derive the standard and general equation of the parabola, first we need to compute for A. Since A would be the distance between F and the vertex, or the vertex to the point D on the directrix, from the figure, we can see that we can compute for A as 4 minus 1 divided by 2, which is equal to 3 over 2. Next is to compute for the coordinates of the vertex, since we'll be needing the coordinates of the vertex for deriving the standard equation. And since the vertex is halfway between F and D, we therefore compute for the coordinates of V using the midpoint formulas. By the midpoint formulas, we have negative 2 minus 2 all over 2 and 4 plus 1 all over 2, which results into negative 2 and 5 over 2. Let's now draw our parabola and derive its standard equation. The form of the standard equation would be x minus h squared equals 4a times y minus k. We substitute the coordinates of the vertex in the equation and the value for a. Then we have x minus negative 2 squared equals 4 times 3 halves times y minus 5 halves. Simplifying, we have x plus 2 squared equals 6 times y minus 5 halves. This would be the standard equation for this particular parabola. To get the general equation of this parabola, we simply extend the solution for the result of the standard equation by performing the square of binomial and the distribution of 6 to the term y and negative 5 halves. Doing that, we have x squared plus 4x plus 4 equals 6y minus 15. Transpose the terms from the right-hand side to the left-hand side, taking note of the change in sign, and then combine like terms. This would be the general equation for this particular parabola. Find the standard and general equation of the parabola with vertex at 3, 1 and directrix x equals negative 1. Let's try to draw what is being described in the problem. It is said that the vertex is at point 3, 1 and the line of the directrix has the equation x equals negative 1. Therefore, we can see from the figure that the distance from point D to point V would be 4 units, which means that the value of A is also equal to 4. From here, we can now derive the standard equation. Since the directrix is located to the left of the parabola and the parabola opens to the right, therefore the form of the equation should be y minus k squared equals 4a times x minus h. We substitute the coordinates of v and the value of a in the given equation. Then we have y minus 1 squared equals 4 times 4 times x minus 3, resulting into y minus 1 squared equals 16 times x minus 3. This would be the standard form of the equation for this particular parabola. Expanding the solution to get the general equation, we'll have y squared minus 2y plus 1 equals 16x minus 48. Make the necessary algebraic operations, then we'll have y squared minus 16x minus 2y plus 49 equals 0. This is the general equation for this particular parabola. We now consider some situational problems involving parabolas. Example: a satellite dish has a shape called a paraboloid, whose cross-section is a parabola. Incoming radio signals, which travel in straight lines, when received parallel to the axis of symmetry of the dish, will bounce off the surface and focus at the receiver. The radio receiver must therefore be placed at the focus of the parabola. How far should the receiver be from the vertex if the dish is 16 feet across and 2.5 feet deep at the vertex? Let's try to illustrate what is being described in the problem. Let's say that this is our satellite dish. The x-axis would serve as our axis of symmetry. Incoming radio signals will bounce off the satellite dish and will focus at F. The line behind the satellite dish would serve as our directrix. The point at the middle would serve as the vertex of the parabola. It would be convenient to put the vertex exactly at the origin, from which we measure the depth of the dish at the vertex, which is 2.5 feet. The dish is 16 feet across, so the edge of the dish would be 8 units above and 8 units below the x-axis. A point P on the parabola would therefore have the coordinates 2.5 and 8. Now, from the standard equation for a parabola which opens to the right, we have y squared equals 4ax. We plug in the coordinates of point P in this equation to solve for a. That becomes 8 squared equals 4a times 2.5. Solving for a, we have 8 squared over 4 times 2.5. That would be about 6.4 feet. Therefore, the distance from the directrix to the vertex would be 6.4 feet, and the distance from the vertex to the focus would also be 6.4 feet. Example: shown below is the famous Golden Gate Bridge in San Francisco, California. It is a suspension bridge with cables that hang in the shape of a parabola. The towers supporting the cable are 1,280 meters apart and about 152 meters high from the bridge. If the cable at its lowest is 9 meters above the bridge at its midpoint, how high is the cable 15 meters away horizontally from either tower? Let's try to illustrate what is being described in the problem. Take note that the illustration is not to scale. As described, the two towers are separated by 1,280 meters, and each tower is 152 meters from the bridge. The lowest point of the cable from the bridge is 9 meters. Putting our origin at the middle of the bridge, therefore the coordinates of the vertex would be at 0, 9. Now what is being asked in the problem is the height of a point P where P is 15 meters away horizontally from either tower, in which case we chose to measure 15 meters from the right-hand tower. Now the coordinates of point P is 625 and y, which is the unknown. 625 on the other hand is computed as 1/2 of 1,280 meters, that is 640 minus 15 meters. For the solution, first we use the standard equation for a parabola that opens upward and plug in the coordinates of the vertex V to have a working equation. And that is x minus 0 square equals 4a times y minus 9. In which case we can simplify into x squared equals 4a times y minus 9 and then use this equation to solve for a. Now to solve for a, we need to find a point on our parabola that we know its coordinates. From the figure, we can see that a point Q, which is on the parabola, has the coordinates 640 and 152. We know the coordinates of Q since Q is on the tower, which is 640 meters away from the origin and 152 meters above the bridge. We can now solve for A. We plug in the coordinates of Q in our working equation. Then we have 1,280 divided by 2, which is the 640 coordinate of Q, square equals 4a times 152 minus 9. Solving for a, we have a is about 716.08 meters. After which we then use these results in the previous working equation for the point P to solve for y. Then we have 625 square equals 4 times the computed a, 716.08 times y minus 9. Solving for y, we have y is about 145.38 meters, which means our point P would be 145.38 meters above the bridge.